Welcome to Part 7 of Competency 10. In this video, we will answer questions relating to calculus applications. Okay, before we begin, let's discuss the problem that we'll be using. It says use the following information to solve questions 1 to 4. Okay, the position of a particle moving along the x-axis is defined as follows. X of t equals 1 over 3 t to the third plus 7t squared minus 3t. 4, this is the interval, 3 less than t, 3 less than t, and t is less than 9, where t represents time. Okay, so for number 1, so we will put this in our calculator and deal with, looks like numbers 1, 2, 3, and 4. Okay, number 1 says, what is the average velocity over the time period from t equals 3 and t equals 9? Okay, what they're really asking for is the slope over that time period. So we don't have to find the first derivative. We just need to put this into our calculator, get those values for 3 and 9, and set them up as slope as we did before. Because what's really going on is your average velocity. That is the slope at that point, okay? So we need to push our y equals and enter the equation. Okay, so I'm going to do alpha, window, go over. I'm using a fraction for the 1/3, if you're wondering. Okay, so number 1's what we want, push enter, and it sets us up. So we have the 1, arrow down, put in the 3, scoot over. Now, we will have to use our x, okay? So then that means that we have x, caret up 3, arrow over like it's telling us when it flashes. So plus 7, and then x, and use our x squared, because that'll arrow over automatically. So minus 3, and then our x. Okay, now let's graph this. Okay, looks like I didn't do that right. It says x to the third. Well, it looks suspicious. So let's zoom out and make sure I have that all in there. Okay, so I'm going to graph it again. And let's say zoom. And let's go 9. Sometimes 9 works better. Okay, zoom 6. Zoom 6 is better. Good enough. It still looks quadratic. Okay, just making sure. Whenever I see something quadratic, but yet I see t to the third, although we have the third, second, and to the first power, I still need to take a look and make sure. Okay, either way, doesn't matter. Okay, so we go second graph. Now, I have this set up in halves. I'm going to have to take all that out. How do we do that? We need to go to second window, and I want to look at whole numbers, so I put in 1, and I enter, and I need to look at whole numbers again, increments of 1, push enter. And I know that right now because I'm looking at the ABCD option, and those are all whole numbers. Okay. All right, so let's try our graph again. And that means for 9, we have, I need 3 and 9. 3 is 63. So this is what we need. M equals, slope is M. We have 9 minus 3. And we're going to have minus 63. Now we need the value of 9. I'm just going to arrow down till I get it. And that is 783. Okay, so let's back out. Actually, just enter that in the calculator. We will need to use parentheses because we have division and subtraction together. So parentheses, 783 minus 63. Close my parentheses, divide, and then parentheses again, 9 minus 3. I know that that's 6, but I enter it anyway, just in case, okay? Now push enter, and it's 120, and that's actually the value that we need. Okay, now let's go to number 2. What is the instant velocity at this value? Okay, for this one, okay, we will need to look at T prime. So this is what we do. We have, okay, go to graph. Took me a second to think about it. Here's our graph. But when it says instantaneous velocity, I know that velocity is that would be x prime of t. Okay, our equation itself is our position or our speed, and x prime or f prime, y prime, first derivative, that's the velocity. Okay, and then after that, double prime, that would be acceleration. So I know I need x prime, but our calculator will do this for us. I have my graph, so I push second, trace, okay, go down to number 6, and simply, and we've done this before in other videos, just go to the value you need. So we type 5 and we enter. And there it is. You see where it says dy dx? That means your derivative at that time is 92. And that actually is the correct value. And I knew that because it said instantaneous velocity and a given point to evaluate. Okay? All right, now. All right, so the next one is, what is the average acceleration? But that's between these two points, okay? All right, but that would be the slope of first. It's like you're going first to do this. First, we needed the slope, and that was using the slope at the speed. Okay, with our position formula. Then to find an instantaneous rate for one point, we used prime. Now they want the average acceleration. So that means we need to use the x prime and the slope of that. So this is what we need to do. I'm going to say m equals, okay, and it says from 2 to 6. So I will use the values of 6 minus 2, okay? And now we need to do each of those just like we did before. We have the correct graph in, so we just repeat our process right here. So I'm just going to kind of start over by pushing graph. Now, second, trace, which is calculate, number 6, but I need the value of 6 first. So I'm going to push 6 and enter. And that gives me 117. Okay. So what we're getting is we're using our instantaneous uh, velocity, velocity. And when we use those to get a slope, that's actually the acceleration. Okay. All right. So now I like to just start over by pushing graph and going second trace, number 6, but I need to just enter 2. Okay, which is 29. So I subtract 29. Okay, so now I can back out of that and just enter it in the calculator. Okay, so parentheses 117, subtract the 29, close the parentheses, divide, open them up again, and 6 minus 2 and close it. Make sure that we have the same thing that we have written down, entered. Okay, yes, and enter, and that is the correct value. It is 22. Okay, so let's look at number 4. What is the average acceleration at that point? Now, this is where it changes, okay? We cannot use the formula as entered. Let me go here. Let me go to my y equals. Okay, here's where we had it entered. We can't use that as entered. That's our position formula. So we have our position. We can use the calculator to go, let's say, to the first derivative. So everything the calculator has been doing for us is getting first derivative values off of the position formula, the given. But now we need to actually go to double prime. So we will have to create that, okay? So let's go to double prime or y prime. If we use the y prime, then the calculator will deal with the double prime for us. Okay. All right. So what do we need to do here? Y prime equals, well, that will be 1/3, 3. That will be x squared plus 14x and then minus 3. Okay. So let's put that in the calculator. Go over, go down. Oh, before we do that, let's turn off the original. How do we do that? If you've watched other videos, we simply highlight it, then push enter. And when I go down to the next one, you see it's not highlighted anymore. So I do not have to highlight this next one. I can just go over and start entering things and it will highlight for me. So let's see, x squared, okay, plus 14x minus the 3, okay? All right, now see it's highlighted, and let's graph, and you'll see it should be the orange color. And there it is, which we aren't seeing the whole thing. Doesn't matter. We just want to know what the next derivative value would be at 3. So what do? Second trace and say 3 enter. Uh-oh, I hit the wrong thing. Go back to graph. Just push graph again. Okay, second trace. I did. I pushed the wrong thing. Sorry. Number 6. Okay, now I push 3. 3, enter. And it says 20, which is the correct value. Okay, you kind of have to get used to the fact that the calculator will only give you the derivative after whatever derivative that is after what you truly have entered in the calculator. So let's go back to the y equals real quick. Okay, so y sub 1 is our original equation, okay? And we could get derivative values for the first derivative from there. But we can't it doesn't give us second derivative values. So what do you have to do if you need anything for the second derivative? Well, you have to actually know how to calculate the first derivative, enter the first derivative, and then you can get calculations off that. Or you could see y1 would be the position, and then y2 is the first derivative. Now in y3, we could simply enter the second derivative, but we didn't need to because we have it. You can and compare if you wish. I'm not doing that when I'm taking a test. I just do the minimum that I have to do it for my brain, and then I let the calculator do the rest. So anyway, let's go to number 5. Okay, number 5. Here, let me scoot that over. Consider the triangular region bounded by the positive x-axis and the positive y-axis, and the line whose equation is y equals 5 minus 2x. A rectangle will be placed inside this region so that one vertex lies on the line. What is the largest possible area for this rectangle? Okay, spoiler alert. I have found out that to optimize, this is optimization, and generally that's the midpoints for the x and y axis. That's generally what gives me that point. But I'll pencil that in real quick and we'll verify it. So the region, the distance from 0 to from 0 along the x-axis is 2.5. And that midpoint will be 5. See, that's 5/4 or 1 1/4. Okay. And then obviously from 2 to 5 is 2.5 right here along 2.5 along the y-axis. Okay. So that should be our point, okay, that we use. All right, but what they're really asking is, it says, what is the largest possible area? Well, knowing that, I probably would just multiply 2.5 times 1 1/4 and see what I get. But let's do this in another manner because you may not get numbers that are that simple. So what do? Let's say we don't know what we're doing, right? And let's call the distance that we need x, okay? Along the x-axis is x, and then along the y-axis, we'll call that y. And let's say we don't know x and y. So for that situation, we need the area. The area equals base is x, height is y. So base times height, okay? Well, we use just the value of x, but for the y, we can use the equation of the line. So this is what we're going to get. Area equals, this is our starting equation per se, x times 5 minus 2x. Okay, so then what we need is an area equation of 5x minus 2x squared. Okay, and that will help us get our optimization. Okay, so now what we do, that since we have that, that gives us our f of x or area formula. Okay, we take the first derivative of that, set it equal to 0, and solve for that x value. When we have that, then we can find our y value in our calculator. Okay, all right, so this is what we need to do. Okay, so that means for, I'll call it A prime, okay? A prime, we have 5 minus 4x. Set that equal to 0. And then we have 4x equals 5. Divide both sides by 4. And, suspicious. That is actually the value of x that we need to get our maximum. It optimizes the area. Okay, so let's put this in our calculator. Let's say y equals, let's clear this part out and just go up to our y1 and let's put in our original equation and see what happens here. Okay, so we have 5 minus 2 and x. Let's graph that. It goes down. Okay, now let's look at our table. Oh, but we need it set up in 1/4 increments. Okay, so we are going to see, because we can't even get our value of x. It's not even showing up. So what do? We go second window, and that's our setup. And I'm going to leave it the values of 1 there. So let's just go to table setup. We already have number 1. Scoot over beside the 1. Now say alpha window, arrow over to our fractions. Number 1's highlighted, push enter. Now we have 1 divided by the 4. Okay, so now we have increments of 1/4. Okay, so let's try our second graph. And there we go. Look at what we have. So that is actually giving us the two things that we need to multiply together to get the value that we need. Okay, so we need to take 5/4 times 5/2 and that'll give us the appropriate area. Okay, optimize area. And like I said, I figured out over doing several of these that you can just go halfway. Okay, but either way, we have what we need. We did it mathematically and we're good to go. Okay, second mode. Second mode, get out of that. Okay, there we go. So we need to take, I'll use parentheses so you can see it. 5 divided by 4, close our parentheses, open a parentheses, 5 divided by 2. Let's push enter and see if it works. Oh, okay. All right, well, let's do this. Let's say math, second, math enter. Yes, so 25 over 8 when we use our math function gives us what we need, and that is option C. So that's our optimized area. That's our maximum area that we could put inside that, with a rectangle. Now, other shapes would be different, but for this shape of a rectangle, that's the best that we can do. Okay? All right, let's go to number 6. Okay? In the ABC company, the cost, which we're going to call C, to manufacture X number of file cabinets each day is given by the equation C equals X to the third minus 33X squared plus 336X plus 100. How many filing cabinets per day should the ABC company manufacture in order to minimize the cost? Okay, this is a minimization situation. And what we need to do here is what I do is I get the first derivative. And then using the first derivative, that gets me a value, a proper value to look at. Once I do that, I put everything in the calculator. So let's do that. Let's put in our position as well as this first derivative, okay? C prime equals X squared minus 66X plus 336. Verify. 2 times 3 is 66. Oh, I forgot the 3. I'll just scoot all that over instead of rewriting it. Yeah, big boo-boo. That's why sometimes you'll hear me pause. It's because I'm looking at what I wrote down again. Okay, and it's a good thing I did. Okay, so let's put both those in our calculator. So let's go to our y equals, clear it all out. Let's put our C equation in for y1, and y2 will be our first derivative, our C prime, okay? All right, so we have x carried up 3 and arrow over minus 33x, square that, then plus 336x plus the 100, okay? All right, let's go down. All right, now this is our C prime, and let's say 3x squared minus 66x plus 336. Okay, and let's graph. Let's see what all this. Oh, before I do that, let me double check my numbers. Looks good. I should be okay. Okay, let's double check. Okay, we get some weird stuff. So looks like to me, and I've already done it, we need to scoot over, we need to move to the right. So let's shift our window. So let's go to our window. And I'm going to scoot over. I'm going to put -2 as our minimum. Okay. Maximum, I think I had to say 20. Yeah, let's put in 20. Okay. And now leave that alone. We need, arrow down. Okay. Now, the minimum. Can't remember what I did, but we'll have to play with this. So the maximum, I think we can set the maximum like at 8. And then let's try negative 20. because we saw that it looked like things were going to go down, okay? All right, so now let's graph and see what happens. Ooh, almost. So it looks like we're not going to get all of that. Pink is our original. The truth is, for this, we really just need to look at the where things change over, which would be our X values here and here, here and here. Okay. So really we could just look at our table for that. Let's see what our table gives us, okay? All right. And then we also need to look at this minimum here down the center, okay? So for that minimum, okay. No, we just need to look at this. Let's see, second graph. Okay. What number were we looking at? And you know what? We need whole numbers. So we also need to go second window and get rid of this and go back to 1 and now go to back to our table. Oh, much better, much better. Okay. How are we going to know where our minimums are? Okay, or our maximums? Okay. Look at the yellow, the 0 value. See that 0? That's what we need to look at. So I see the 8. We go back to the graph. If you count your graph, 1, 2, 3, 4, 5, 6, 7, 8. But I really don't think, because they're asking to minimize the cost, okay? Let's compare that to the actual cost function. It's either going to be at 8 or 9, 10, 11, 12, 13, or 14 looks like. Okay. So let's look at 8, and we said, looks like that isn't a minute. Look at your P. I don't think that's minimizing. Looks like we go up and then we go down. So that looks like a maximum situation at 8. Okay. So then let's go down to, we said go over to about 14. Okay. I'm going to go down a little more. Okay. Now there's our 0. Okay. Now notice that we have 1080. And on one side, it's 90. And then for 15, it's 90. And then it keeps on going up. But then on the other side for 14, let's see, 14, it's down and then it goes up, up, up. So it looks like we actually do have a minimum value at 14. So where that 0 is the value of 1080 for X is 14 seems to be what we need. And let's look at our ABCD option. And negative 14 and negative 18 weren't even in the running. 8 was a maximizing. It went up. But A actually went down. And on either side of A, if the X value is going to left or right, are the values for actual parent equation are going up. Okay, or original equation, I'm sorry. All right, so let's see if we can zoom out. Let's just out of curiosity. So it's always worth it to see. So there we have a decent setup. And our graph our table showed us a lot. But let's say zoom and let's zoom out. Number 3. Let's zoom out. Yeah, that's good where I have it. Enter. Not telling us much. No. This is a situation where you have to do it numerically or go online and put it into GeoGebra or another graphing calculator online that's a little more powerful. That doesn't help us during a test, so we have to do it numerically. Okay, number 7. Air is blown into a spherical balloon at a rate of 4 cubic inches per minute. Okay, per minute is time, okay? All right. At what rate, okay, and the word rate is important. At what rate is the radius changing at the instant that the radius is 3 inches? Okay. All right. This is, we will have to get the first derivative. Okay. And we know that our rate for, it says air is blown into the sphere. So don't confuse rate with radius. That's one thing that, okay. Well, I'm just going to use the whole word rate. R-A-T. Just use rate, and we're going to say that equals 4t, okay? 4 times whatever minute, however many minutes that actually is, okay? All right, now we know that volume, the volume of a spherical balloon is 4 pi r to the third over 3. Now, if we're talking about rate and rate of change and an instant, that screams the first derivative, v prime. So we know that when we do that, the first derivative of the volume is the surface area, and I already know that that is 4 pi r squared. Now, it says at 3 inches, so I will put v prime 3, okay? We're going to calculate that, and that will be at 3, that's 3 squared. So this will be 36 pi, okay? So that at least gives us that instant rate, okay? But it doesn't answer the question. It says radius is changing. At what rate is it changing? We have that volume at that time, but it doesn't help me with that radius, okay? So this is just something that you're going to have to remember how to do, okay? Now, we have volume at the first derivative. We need the rate at the first derivative, okay? So that rate is actually 4. So we're using R prime 4, technically, okay? So what do? We take and put, actually, let me just erase that. And I already have it circled, rate of 4, okay? So we take our rate, actually, we take our instant situation here. So we have this rate, 36 pi, and then it's going to be times that radius, that rate of the radius, okay? And then that will equal 4, okay? Right. Okay, so we solve for this radius, change of radius, our derivative of r, okay? R prime, but in this situation, this is the change of the radius, okay? All right, so what do we have to do? We literally take and just divide both sides by 36 pi. Sorry about that. 36, not 63. 36 pi, right? This cancels out. And simplify. Well, that's going to give us 1 over 9 pi. Okay. And in this situation, we couldn't pop that into the calculator to get our final solution because they are in terms of pi and not decimals. Okay. So obviously what we need is option A. Okay. Now let's put this in our 4 pi r squared in our y, and let's see what we get. Okay. All right. Okay, let's take a look at what that looks like. All right. I've put them both in there but to be honest, this just proves the fact that this really doesn't help us using those same techniques that we had. It's in this situation, we're better getting it on our own by hand because let's graph this and now let's use our second trace, number 6. Let's do at 3. Okay, now let's enter and it doesn't give us that value that we need, that rate of instantaneous rate of change. Okay, all right, this is the last question in this video, and again I have to say thank you for watching. Thank you for all your shares and your likes and your subscriptions. Happy testing.